the sum of random variables. We did the sum of random variables using a technique. What is that technique? Do you remember? It was on the exam. If you had n IID random variables, you want to sum them and find the density of the sum. Not the density, but the MGF. Right? We converted the sum to an MGF. And what we know is that the MGF is unique to a density. It is, since it is unique, once I come up with an MGF, I can easily match it to known MGFs and identify the distribution. It's a, sort of recognizing the pattern of a density. Well, sometimes you may have two random variables. Let's just say that they're independent. But the process that I'm going to do, they don't have to be independent necessarily. And I'll show you the exact step where we can get into that. So X and Y are IID random variables. Fx of x and Fy of y are their densities. Yes. Then what would their joint density equal to? The product of the individual marginal densities. Right? With me so far. Now, let's say I have u to be x plus y. The sum of two random variables. Mind you, the easier way would be to use MGF. Makes things a lot easier when you have a whole lot of random variables. We want to find the density of u. Find the density of u. All we have to do is take a mass and divide by volume. Moving on. So how do we find it? We make use of the joint PDF. So u is x plus y, and v, I'm going to call it x. The reason being I have two variables. The transformation that I have is a bivariate transformation. The last two transformations that we did, location, scale, and square root transformation, they were univariate, right? Here I'm using two variables and trying to come up with a third random variable. Binary, so we need the joint PDF. So if V is X, then I could write X plus Y as V plus Y, correct? Which would simply mean Y is V minus V. Over here, X is equal to V. Ah, okay. I need to go back to algebra. U minus V.
So it changed from the full to the capital U to the lowercase u, so it's specified.
Still uppercase U. If you recall, last time we did this, we had f of y, and we wanted to use the density of x. And then we did something over here. What was that? The derivative of whatever function that I had inside. So the derivative of that function went here. Chain. Now that is in one dimension. Here, going to have u, v, there has to be a derivative here. Agreed? In two dimensions. What should go there? Cut through.
Yeah.
Getting the partial derivatives, but we can't just add them. I don't know if they went over this in Calc 3. So did you guys hear about the guy named Jacob?
Oh, yeah.
The Jacobian, right? So you've got to take the absolute value of the determinant of the Jacobian. So that's the absolute value. The Jacobian is itself a determinant, correct? So the matrix, we just have to take each variable and take the derivative with respect to u and v. So if I take the derivative of x with respect to u, I'll get 0. With respect to v, I'll get 1. The derivative of y with respect to u is 1. With respect to v is minus 1. The determinant is negative 1. Absolute value of that matrix. I'll write it as determinant of J to avoid confusion. Because I know some call J to be the Jacobian, some call the determinant of J to be the Jacobian. Absolute value of negative 1 is 1. X and Y. Now I can switch over from uppercase x to lowercase x, uppercase y to lowercase y, uppercase u to lowercase u, uppercase v to lowercase v. So what is lowercase x in terms of v or u? V. What about Y? U minus V. So that is the final joint PDF that I have. So that is the joint PDF of U and V. Yes, that equals F of U comma V. Good so far. If you have the joint PDF, how do we get the marginal PDF? We have to integrate with respect to one of the variables. Okay. We want to find the density of U. So we have to integrate with respect to what variable? V. So Fu of U was intentional. I was waiting for this moment. So we have to take the joint distribution and integrate it with respect to V. I will get the density of the sum of random variables. So standard formula, if we can find the joint PDF, you have the answer. But here we know we have independence. So we're going to use that. And I can split it up, correct? Fx evaluated at V, Fy evaluated at U minus V. Oh, V. Good. So this integral that you see occurs, I can switch x and y, call it as, y and x, and change the transformations accordingly. Doesn't matter. But this form that I have, two different functions, or same function, but they U minus V integrated over V. It's called the convolution of the function f x and the function f(y), also known as the convolution integral.
So that inverse just wrote the integral that we all that itself is a convolution.
This part right here. So if you don't have independence, you're just going to integrate it using joint PDF. That is the only one. But if I have independence, then I can split it up, and that is what we call the convolution integral. That is for two random variables. You sum, you end up getting the density. What if I had n random variables, IID, sum them all together, call it U, and I want to find its density. So, how many integrals would you need? N random variables,
So n divided by 2.
n divided by 2, n minus 1, right? You need n minus 1, and it's a huge convolution integral. Do you really want to sit and do that? Absolutely not. Not only that, j is going to be n by n, right? So everything's going to get complicated when we have multiple variables. So what is the easier way when you have n IID random variables? The one that I started this particular topic with, moment generating functions. That is the easiest way to find the density of some of IID random variables. If it is just two of them, sure, I can do this. Convolution of x and fy, life is great, but you have too many, then that's a problem. Have you guys had a Fourier transform? No? So this convolution would reduce to a simple product in the Fourier domain. That is also an easier way to do or find the density. Are we clear? Yes.